Blazej Kubiak. I'm Krzysztof Kudrynski. And this is a drone. Now it's in the box. And the world consists of two groups of people. People from the first group will immediately take the drone out and start to enjoy flying, while people from the second group will immediately download the API. Now, there is absolutely no shame to be part of the first group. I have real friends that would actually do this, and they are nice people. Myself and Blazej, we are proud to represent the elite. After over 2 years of dealing with this drone, we have absolutely no idea how to manually fly that thing. In this project, the drone will learn to fly. And it will learn that skill based on what it sees, and it will see the world by a monocamera. So a starting point of our project will be a calibration chessboard. By making a lot of pictures of such well-structured image, you can quickly find some mathematical algorithms to correct all the distortions and calibrate the parameters of the camera to make everything look nice and smooth. In fact, calibration chessboard is a starting project of almost every project in computer vision. And then you move on with simple projects like detecting chessboard in the image, then maybe tracking chessboard in the video. These are the hello words of computer vision. But if you are here to see the hello world application, you might be a little bit disappointed. Although we cannot disagree that tracking chessboard has so many wonderful real-life applications, ranging from detection of freaks still playing chess on a chessboard, up to detection of people walking on the street with a chessboard. And the list does not end here. However, our project is inspired by something completely different. And these are extracts of a few videos of drone racing, and I think you can feel that speed. It's so amazing. And when you realize that actually these drones were controlled manually, I'm sure there is one word screaming in your head, and it is irresponsibility. Let us analyze this one case again. This is a word seen by a drone camera during some race. And you can already know what to do. You can turn a little bit left and go fast through the tunnel. There's still a lot of time, but if you are starting to worry now, you are doing the right thing, because although there is still a lot of frames to turn, I feel you already know how it's going to end. While you can see, there was so much time to react. So much time to react before these silly crashes. So many frames which were just begging for salvation. Together with Blazej, we decided to put an end to that. As a user, you should only select where you want to fly, and it is the machine that should calculate all the low-level controls by analyzing the image. And today, we will think how we could develop this. We will have a walk through all of the steps needed to attain that. And we will show you how it worked on our example. But in our example, instead of the ruins like that, instead of the forest and parking lots, we will show you our tests from our modern TomTom office, built and opened this year. But if you look at it at the right perspective, you cannot miss the similarity. So such similarity cannot be a chance. I think we were destined to make this test in the office. Okay, so let's start with solving our task. And for initial inspiration, let's analyze this case again. And we all have to agree that we humans are just amazing. Everyone here immediately and without any effort will be able to spot the right place that is worth flying to. Everyone here immediately and without any effort will be able to plan the next actions. And everyone here immediately and without any effort will be able to spot the emerging collisions and act accordingly. This is already amazing, but what is even more amazing is the fact that with the exactly same brain, exactly at the same time, we humans are able to plan our next meal and perform deep considerations about life. And well, such general intelligence is still not beyond the reach of science, so today we'll not talk how to make drone cook or understand life, but we will try to analyze how we humans would perform these three particular tasks, and because the machine can be perfectly focused on them only, we will soon find that it's working faster and will outperform human. Okay, so let's start with some basics. You can start with whatever equipment you want, as long as you can control it from your own software. And our system was based on Parrot Air Drone 2, and there is a lot of, you can communicate with it over Wi-Fi, and there is a lot of software in the web which you can download. We used Yadrone framework, which is open source under Apache license, so you can just download it. And out of thousands of lines of codes of Yadrone, we used just one line code, especially move command, where you can specify the tilt angle in both directions, X and Y, the change of speed in the Z direction, and the rotation speed. So this, you just apply this, and the drone will move as you would like to. And these parameters will be derived from the understanding of the image that is decoded for us from our camera. And it was the most convenient for us to use the C++ FFmpeg to decode the stream, and then analyze the image using Python libraries like NumPy and OpenCV to analyze this image. And finally, the control center to orchestrate all that, we initially planned to write it in Java because Yadrone was also in Java, and such system is a nice place to start. But obviously, as we will move on during this presentation, we will evolve our ideas, and you will see that this architecture, this design, will change gradually as we speak. But it is a nice backbone, so let's start with the logic. So our first level of autonomy is tracking. And let's think how to implement tracking on the machine. We would like to track this place while we move. And because we are fans of the human brain, let's think how we humans, how our brain works in real-life situations when we want to do that. And let us think about a real nice example when we go to the club and there is a lot of people and we find something catchy, something that captures our eyes. For example, a hat. Yeah, but before we focus on the hat, let's imagine a situation, but you must imagine it really hard, that instead of a hat, we have a chessboard. Well, this does not happen very often, but if it was the case, we could use our predefined chessboard tracking algorithm to accomplish our task. Unfortunately, sometimes it happens that we have to track something else, and it is at this moment that this region gains some description. It may be the distribution of colors inside this region. We may be following the shape of the HUD itself, or just try to follow the movement of the pixels. So all of these approaches can easily be implemented on the machine, and the good news is that you don't need to do it on your own because you have frameworks. For example, OpenCV library, which is a C++ library, but with wrappers in Python and Java, so you can nicely use it. And out of quite a lot of algorithms, we tried three of them. In MinShift, you are just specifying a region, and then you are trying to shift and scale this region so that the distribution of colors stays the same. It's done automatically for you. In CamShift, it's very similar, but you can also rotate the image. And finally, in optical flow, you will be analyzing the movement of individual pixels in the image using some nice mathematical tricks around Taylor expansion and so on. And we find out that in our case, we made some experiments, and optical flow gave us best results in this case. So let's see how it works in action. What you can see here is our graphical user interface. So you can see what the drone sees with some controls. The thing on the left, the arrows on the left and right shows what movement needs to be taken so that we omit an obstacle. Similarly, the bottom arrow shows if we need to fly higher or lower to omit the obstacle. But in the beginning, obviously, they will, in the first level of autonomy, they will be all 0 because we are not yet omitting obstacles. What will be most interesting for us is the red circle in the middle, our circle of focus, attention. It is by default in the middle, but when we start flying, we will click on the table on the left, and the drone will start to track this place. And then finally, the arrow on the top shows what rotation needs to be taken so that the drone actually is focused, centered on the clicked region. So let's start flying, and you can see we clicked on the table, and it is being tracked. And you can see the strong desire of the drone to turn so that we can focus on this table. So when we, in our graphical user interface, when we press 1, we'll go into level autonomy number 1, and you will see now the drone is floating freely with tracking of the object that we have that is being tracked. So this is our level autonomy number 1. So if we want to increase the autonomy level 2, which is just giving action that will fly towards this place, it's quite obvious, we'll just fly forward. But in real life scenarios in the office, it's not only always a good idea to implement that straightforward. So we decided to quickly move on to the level 3 autonomy, which also avoids obstacles. And this is where the fun begins. Because in order to avoid risks, you need to understand and identify in 3D space the obstacles, which you can see in a 2-dimensional image. And that seems difficult. So the question we can ask ourselves again is how we humans would do it. How do we humans understand the space around us? And probably first answer that comes into our head is through the pair of our eyes. So let's say this is a simplified diagram of our viewing system. The blue rectangle is the place where the image is formed, so the retina of our eye, and the dashed line is its principal axis. Now, a single pixel in this plane would tell you very limited information about what we see in the world. In fact, it will only tell you the ray on which the image lies, on which the object lies in the world. Unless you have another eye, which is quite common, and in the another eye, you have a pixel corresponding to the same object, and then, using some simple maths, you can actually find the place in the world where this object lies. So, Is stereo vision an answer? It may be. We could just add a stereo vision system to our drone instead of a mono camera, which would be more expensive and much more heavier probably. So instead, before we all go shopping, let's think and ask ourselves another question. Is it really necessary? Are we humans hopeless when we have just one eye? Obviously not. In fact, when we move, our eyes feed the brain with images, with a lot of images, and it can be proven mathematically that if you have at least 7 pixels, corresponding pixels in 2 images in some non-critical configuration, you are able to reconstruct both the movement and the 3D structure that we are looking at. Up to scale factor, obviously. So, for example, this will be a video of my chair using these mathematical tricks. And in this image, in this algorithm, in each image, there will be some key points detected by the algorithm, and they will be tracked, so we have the correspondence within the next frames. And finally, it will calculate the 3D image on the fly, which you can see now being done. The approach is known under many names, mostly structure from motion, multiple view reconstruction, or visual SLAM. There is an OpenCV, some functions for this, with which you can do some basic reconstruction. But there are also many projects in the web, or there are many great books if you would like to understand it and maybe write your own better code. And if you do it right, it will work amazing, especially if you move horizontally versus the objects that you are trying to reconstruct, because at every frame you will give a lot of different perspectives for your image, for your object to be reconstructed. However, if you, for example, only fly towards the object, you might have a little bit of a problem, because every frame you add, the image will be very similar. There will be no different perspective of the objects that you have, especially those in the center of the image. And projectively, this will give very few additional information. And in fact, because there is some noise in the sensor, there is still some miscalibration, this noise might be bigger than actually the projective information that you give. And then you might think that your 3D world is flat. And that is not true. Okay. Anyway, if we just rotate, that would be even worse, because in this case, we have only one point at which all rays meet, and there is no additional projective information, which is the worst case. And in fact, when we are racing with our drone, most of the time we'll fly forward and rotate, which is the worst case scenario for this method, although, however beautiful it sounds. A similar approach, but a little bit different, would be to use optical flow itself. So let's focus on the door handle and the glass while we will move. And you can see that the glass, which is closer, moves faster on the image than the door, which is far away. And we could use this information to say something about the space, which is farther away. So we could, in fact, track all the objects and create our 3D image. But again here, similarly to previous method, it is best if we move vertically, horizontally, whatever, you know what I mean, towards what we see, which is not good. Of course, we could think of a situation where we could, in fact, use that, and we would, to our drone, we would deliberately add some motions to the sides as we fly. And for us, Polish people and our friends in Russia, adding a little bit of salamic path would be perfectly excused, but we would not win the race that way. So again, are we doomed to fail? Absolutely not. And again, we will draw inspiration from the power of the human brain, because we humans do not need two eyes to understand space. We don't need even to move around. We can stand still in one place with one eye open and still have no doubt what's around us. And how do we know that? From experience. From billions of images fed into our brain during our lives, we learned to understand objects, their perspective, their relative sizes, their arrangements, and their shadows. With our lifetime experience of looking at the world, we humans have absolutely no doubts. We need no tricks to see the space. And as amazing as it may sound, we can pass this experience to the machine with the new advancements of artificial intelligence. So we will try to train our drone using deep convolutional neural network. In a few minutes, Blazej will tell you more about that. But if anyone here is absolutely unfamiliar with the concept of machine learning, the idea is that instead of designing the set of precise algorithms, formulas, and rules, as we do in conventional handcrafted algorithm, we design a mathematical multi-layer model capable to use all the given input in its raw format to give some output label. And to make it a correct label, we flood it with thousands of examples so that we will tune the reactions to each pixels and combinations to these reactions and combinations so that finally you have the output pixel as you want it. So you can read a lot about AI, but today we prepared something better for you. You will be part of an amazing experiment which will give you a better feeling of how AI works, and more importantly, putting some light on a few concerns of its proper usage. So, in this experiment, you will be the AI, and I will train you to perform a simple categorization task. As every network, in the beginning, you have absolutely no idea what you will be learning, and I will just give you examples without any explanation with labels. And after some examples, you will train to shape your brain so that finally, when I give you an example of which you see for the first time and you have no idea what it is, you will know what to answer. Are you ready? Okay. Image number 1, label. Image number 2, label. Image number 3, label. Image number 4, label. The training time is over. Now it's time for the ultimate test. Please don't hurry up. You have a lot of time. And make sure that allowed answers are yes and no. So, the test is. Oh, come on, wait a second. Please now raise your hands. Who votes for yes? Okay. Now please raise your hands. Who votes for no? Beautiful. The results are 5,035 for yes and 1 for no. Ladies and gentlemen, this is a correct answer. Ladies and gentlemen, we just successfully detected a sofa. So thank you very much for your contribution. Without your votes, this would be impossible to make this experiment. We won. We are very happy. We are millionaires. We won this competition. However, there is something disturbing. There is this one guy who was absolutely blinded by some other less important features also available in this image. And if we had more animal lovers in this room, we would miserably fail to detect a lovely sofa. And seriously now, this is a real concern in AI. Preparing a good, precisely shaped training set, unambiguous, is an art. And usually you will still not know exactly what the algorithm, what the network learned. So you usually need a huge training set to make that happen. And sometimes, as a designer, maybe you can make a choice to afford a much lower cost an algorithm which you can intuitively find some nice rules and formulas for. In our case, our handcrafted algorithm would be a pain, because what we want is attaching a third dimension to an image that has only 2 dimensions. So let's say a depth. Here it is coded by color, so if we were able to make this image out of every frame that we get, then we will accomplish our task. And finally, we will just detect some black regions and act accordingly to omit them. In our case, we will be using a deep convolutional neural network to achieve that. But in order to train a network, we need training data. In other words, if we want the machine to get this depth map for every incoming frame, we first need to show it 100,000 of examples of this job done right. So where to take this data from? One way to do it would be to take a ruler and for every pixel in the image, measure the distance between our camera and the object in this pixel. Repeat it for every pixel, and then repeat it for every image we have. According to our rough calculation, the time needed for that would be 1,729 days. So we decided to use a different approach. If we come back to our structure from motion algorithm, you can remember it works well while moving sideways, but it works a bit worse in other cases. But during training, we don't care. We can prepare a nice scenario of our drone moving sideways to our objects, and then some nice scenario that move, for example, from 0 to 4 meters to and from of the pillar. For example, that's why we call it deep pillar learning. And then you are able to actually use structure from motion to produce depth maps for you, which will be your training set for your network. Now, this will be only up to scale, as I told you, and the scale will be floating. So what you can do more, you can put a histogram of every pixel in time. You can locate the pixels corresponding to the pillar, and then, because you know it's from 0 to 4 meters, you can normalize it and apply this normalization back to the image so that every frame gives you a proper metric distance in your depth map. And that's how you can create your training set to train your machine. And in fact, we have to tell you we are in love with our idea. However, you have to know that there are much faster ways to achieve the same solution. And now Blazej will tell you more about these ideas and about deep convolutional neural networks.
Hello, everyone. So it's great to make great things from scratch. However, sometimes it's much wiser to use existing solution. That's why we use deep neural network already trained for depth estimation. We found that in internet. And what was really nice, not only in the network structure, but also the model was available to download from GitHub. It was available in 2 formats. We use TensorFlow model. It is more popular and easy to use. What was really nice, authors of the paper also prepared a script that we could read and learn how to load the model, how to fit with our custom data. So after downloading all the stuff, we did first test. And we were a bit scared because the model size was 200 megabytes, loading time was 5 minutes, and the estimation took around 30 seconds. So it was not acceptable for our real-time solution. But fortunately, we found out that we have very powerful machine in our TomTom office with two GTX Titan X graphical cards, and with that equipment, we could achieve 100 milliseconds, which was really acceptable for our system. We have everything which is necessary for further development, but we are guys that won't really know how it works, what is under the hood. And I will try to explain this now, share this knowledge with you. So the solution can be described in the sentence: deep, fully convolutional neural network with upscaling layers fine-tuned from residual network 15. And because it sounds a bit terrible, I will try to explain it in parts. So let's start with neural network. So probably everyone has seen such picture. It's fully connected neural network where every neuron is connected to every neuron in previous layer. There are connections that have weights, and weights are adjusted during training process called backpropagation. So why can we just use that network, feeding the network with image captured by drone camera? So you see that the picture is downscaled to 100 by 100, but even though if we use such network, we have billion weights in that network, which means that every training iterations we would have to update billion weights. It's simply impossible to converge to proper solution with such network. That's why we are using convolutional neural networks. And to understand that, we need to know a few concepts. First is convolution. This is a simple operation where on the left we have the image, and on the right we have the kernel or filter sometimes called filter. And what we do for each part in the frame, we calculate sum of product values between pixels in kernel and pixels in frame. So this is a simple example. Kernel has minus 0, 2, 0, and 0, 2, which means that it will try to expose edges in the image. And after convolution, you see that that edges are better visible in the image. Second concept that is used in convolutional layers, in convolutional neural networks, is max pooling. It is used for size reduction, for downsampling. And it is very stupid operation that takes maximum value pixels and put it in the output. Why it is working? Because we assume that most valuable information is stored in maximum value pixel in feature maps in the network. And actually it was verified in experiments that it works well, and such simple operation could help us to reduce size of the image or feature map. Last concept is unpooling. It is also quite stupid because it is used to upsampling, and we just take the pixel from the input and put it in the left upper corner for each 4 pixels in the output. So the question is why these all zeros are somehow necessary in the output, and actually they are not important, but we always use unpooling layers interleaved with convolutions. So we'll have interpolation between all these pixels, and we have the smooth output for further processing in the network. Usually in convolutional networks, we use rectified linear unit as activation function. It is very simple function that is almost linear, but for negative values are set to 0. And we can think about this function as simplest possible nonlinear function that can be used to add some nonlinearity to the network. So how convolutional layer looks like? So we have the input image or input feature maps. We have a set of filters, the same number of filters as number of channels. We convolve them and sum together. We apply activation function, and we have the feature map. If you want to have multiple feature maps to extract many different features, we have to have multiple set of filters. So what is the difference between convolutional layer in fully connected layer that I was mentioning before? So main difference is number of weights. So we created feature map using just 27 weights stored in this filter. So we have 3 filters, 3 by 3, so it's 27 weights. If you want to have multiple feature maps, like 100, you have like 3,000 weights, but we are producing 100 feature maps, so many, many features. On the other hand, in fully connected layer, we will have 300 million weights, producing just one image. So what is important, the convolutional layer is very good to producing feature, to creating features, and fully connected layer is good to aggregating information and is used for classification. What is also important, fully connected layer is not local, so it consider every pixel that is in the input. And on the other hand, convolutional layer works locally because the filters, convolutional filter works locally. It can be quite big, so the context may be quite huge, but still it is local. So this is typical picture of convolutional neural network. So first part is feature extraction. It consists of a few convolutional layers and max pooling layers. A second part is classification, which consists of a few fully connected layers. However, these days it's quite popular to remove classification part at all, or fully connection part at all, and exchange it with another convolutions and max poolings to have just one pixel at the end. This is a nice trick to even more reduce number of weights. So we have a lighter model. But for our case of depth estimation is not enough, because for an input image, we have just one pixel output, but we want to have full resolution depth map for our input image. That's why we need upscaling layers. So if we add a few upscaling layers interleaved with convolutions, we have full resolution depth map at the end. It is quite difficult to train such a big network from scratch. So it is a nice trick to use, which is called fine-tuning. So it works like we take the we take the model of the network that is trained for completely different tasks, like classification, cats and dogs. And we cut off some layers at the end, and we add another layers, and we retrain the model for our new case. And it can be trained adjusting a little bit all the weights, or we can even freeze the layers that are at the beginning of the network, because in such a big networks, these first layers produce very universal features like edges, etc. And the authors of the paper did exactly this thing. So they took residual network 15, trained it for some other task. They removed classification part. They added upscaling layers and retrained the network for depth estimation. And results are quite amazing. So as you see a few examples, there is RGB image and ground truth picture in the center, and depth prediction on the right. So it is maybe a bit smooth, so edges are not so sharp, but for our case of collision avoidance, it's really enough, or even more than enough. So now Chris will tell you more about our system.
Okay. Hello? Yeah. Okay. So let's come back for a while to our initial system design, which is already a little bit complicated with the components for convenience written in different languages. But now, when we add our deep neural network prediction, it becomes even worse. Because not only do we face porting everything to a Linux machine, but also with a CUDA support, obviously, But also we cannot just call Python scripts independently every time a new frame comes, because we would need to load every time a 200 megabyte model every 30 milliseconds. That would kill us. It's obviously solvable. There are people capable to manage all the possible pieces and make them work as a perfect unity. For those who cannot, the world brings microservices. Of course, these are not the perfect example of microservices, but breaking our design into client-server components made our life much easier. And now the headquarters of our application is our Python application. It requests images from the video decoding service. It analyzes them with the help of the CUDA server, which sent a frame will respond with the depth map. Then we have a Python app, which has the graphical user interface for the user, when you can decide which level of autonomy you will be using by just pressing keys. And then depending on that, either manual or automatic commands for the drone are served to the client, which communicates directly to the drone. Okay, so finally, having all the puzzles solved, it's time for the ultimate demonstration. And we are very happy to be able to show it to you today, because during the day of recording this presentation, this flight, we had a fire. If you don't know what a fire is a set of failures that every self-respecting developer should experience during the day of delivery. And we had that. You will not see this in this demonstration, because we are using the most secure delivery platform statistically proven to be PowerPoint. Now, seriously, the pieces work perfectly stable, but we had some problems with the communication. That's why the video which we are going to show you is probably the best out of 10. But I think you will enjoy it. So let's start. Okay, on the right side, you can see our drone flying. On the left bottom, you can see our artificial brain showing us the depth maps. And depending on if the blue color emerges, then the arrow shows that action needs to be taken to actually omit the obstacle. So on the top left, you can see the red circle, which we clicked in the beginning so that the drone would fly autonomously through the whole way up until it reaches the window. So as you can see, everything is controlled automatically. The deep network plus some algorithms decide how to fly the drone until it actually finishes its flights at the window. In order to prove how repetitive is our process, we will show you the same video again. But now you can focus on the details and watch it in peace. So, according to the task defined in the beginning, we have a full system where a user only shows where they want to fly, and the machine tracks that place and applies some controls using its self-learned experience. It avoids collisions. Everything using a monocamera image only, which is a conclusion of our today's talk. That's all we had to show you today, but in our final words, if we offended anyone while we tried to be funny, please accept the following rectifications. First of all, dogs are more lovely than sofas. Second, not all chess players are freaks. When you actually take your old, good, traditional chessboard, chess can be a nice game. And finally, irresponsibility is fun. Two rules to remember are, first, watch out for the lamps in your office. And second, if you happen to record a video of your drone, for example, crashing into the workspace of your boss, never show it in public. Thank you very much.